Baltimore, Maryland. The Space Telescope Science Institute. It's 2:43 inches the morning, and a planetary scientist sits alone at her workstation. The building is silent, the corridors empty, her team gone hours ago. She stayed late because the James Webb Space Telescope's data pipeline finished 40 minutes ahead of schedule, and what appeared on her screen was something she had never encountered in 22 years of studying planetary atmospheres. This was no ordinary image. It was a three-dimensional map, a meticulously stitched collection of over 1,000 spectral slices forming a vertical portrait of a planetary atmosphere, extending 5,000 kilometers above the cloud tops. A world revealed in depth, for the first time in history. Her eyes widen as she examines the temperature profile. She runs it once, then again. The heating peak and the ion density peak appear at completely different altitudes, separated by thousands of kilometers. Two independent processes were at work, operating simultaneously in regions no existing atmospheric model had ever predicted. She pulls up the 3-decade cooling record of Uranus, and the anomaly is still there, ongoing and unexplained. Sitting back, she feels a mixture of awe and unease, the unmistakable realization of a scientist watching a trusted model collapse under the weight of new, irrefutable data. With deliberate keystrokes, she types 4 words into the team chat: "We need to talk tomorrow." What the James Webb Space Telescope revealed about Uranus, long thought to be a cold, static, and unremarkable ice giant, wasn't confirmed. It was a systematic dismantling of everything humanity believed it knew. Through the lens of theoretical physics, energy transfer in ice-rich atmospheres, and the influence of planetary-scale magnetic fields, this data posed a challenge far beyond Uranus itself. It questioned the models we've used for decades to describe the most common type of planet in our galaxy. To grasp the significance, we must return to humanity's first close encounter with Uranus. January 24, 1986, NASA's Voyager 2 spacecraft completed the only close flyby of this distant world. Launched in 1977 on a trajectory exploiting a rare planetary alignment that occurs once every 176 years, Voyager 2 had already visited Jupiter and Saturn. Its encounter with Uranus lasted only days, a fleeting window in a journey spanning decades. Even so, the spacecraft measured the planet's fundamental properties with precision no Earth-based telescope could match. At first, Voyager 2 appeared to confirm the textbook view. Uranus was a cold, static world. The upper atmosphere registered -224 degrees Celsius, the coldest in the solar system, even colder than Neptune. Yet, this anomaly, Uranus being colder than Neptune despite receiving more sunlight, was largely overlooked. Voyager's instruments painted a planet in thermal equilibrium, radiating the minimal solar energy it absorbed. The broader impression was stability, a quiet, unremarkable ice giant. That picture began to unravel in the early 1990s. 5 years after Voyager's flyby, ground-based observatories monitoring Uranus's upper atmosphere detected a continuous cooling trend that no standard model could explain. Year after year, the upper atmosphere's temperature dropped steadily across a dataset now spanning more than 3 decades. Understanding why this was extraordinary requires a brief dive into thermal equilibrium. Every planet absorbs sunlight and radiates energy back into space. For a planet like Uranus, so far from the Sun, that it receives roughly 370 times less flux than Earth, thermal equilibrium should stabilize relatively quickly, then persist. A continuous cooling trend defies this principle, signaling an active mechanism siphoning energy faster than the Sun can supply it. For 30 years, that mechanism remained a mystery, not for lack of trying, but because Uranus is so distant. Its upper atmosphere is faint, diffuse, and difficult to resolve. The cooling anomaly lingered in scientific literature like an open wound, confirmed but unexplained, a literal cold case. It remained so until an observatory arrived with the sensitivity to peer through Uranus's atmospheric layers, mapping vertical structure from the cloud tops to the ionosphere thousands of kilometers above. That observatory was the James Webb Space Telescope. What Webb revealed over 15 uninterrupted hours of observation was not a solution to one puzzle. It was the beginning of a far deeper mystery. Webb's technical achievement was unprecedented. A 6.5-meter gold-coated segmented mirror, nearly 3 times the size of Hubble's, positioned at the Sun-Earth L, 1.5 million kilometers from Earth. Its 5-layer sunshield, each thinner than a human hair, kept its instruments below -233°C, essential for resolving infrared signals invisible to warmer telescopes. The critical instrument for Uranus was NIRSpec, the near-infrared spectrograph. Unlike a camera, it performs integral field spectroscopy, capturing spectra across a two-dimensional field of view simultaneously, producing a data cube where every spatial point contains full spectral information. From this, researchers extracted chemical composition, temperature, particle density, and motion, layer by layer, across the planet. Over nearly one full rotation, the team gathered over 1,000 spectral slices, detecting the faint infrared glow of H3+ ions, triatomic hydrogen molecules formed when cosmic rays or energetic particles ionize molecular hydrogen. H3+ is a crucial diagnostic molecule, highly sensitive to temperature and density. Mapping its emissions allowed scientists to assemble the first true three-dimensional map of Uranus's upper atmosphere, spanning from the visible clouds to the ionosphere 5,000 kilometers above. For 30 years, Uranus had presented a flat, two-dimensional face. Webb transformed it into a volumetric dataset, adding the critical third dimension that revealed the planet's hidden anomalies. When the team analyzed the temperature profile, the results were both illuminating and unsettling. Voyager had suggested a uniformly frigid atmosphere near -224°C. Without vertical resolution, a single measurement blends multiple layers, leading to the assumption of uniformity. Webb shattered that assumption. Temperatures between 3,000 and 4,000 kilometers above the cloud tops soar to approximately 150°C. Not hot by Earth standards, but a nearly 400° difference across just a few thousand kilometers of atmosphere is extraordinary. This vertical temperature gradient is more than just a number, it is a direct contradiction to what physics predicts for an ice giant receiving so little solar energy. On Earth, upper atmospheric heating occurs in the thermosphere through ultraviolet radiation, producing temperatures of about 1,500°C at peak solar activity. Uranus, by contrast, receives 370 times less solar flux than Earth. The positive 150°C reading cannot be explained by sunlight alone. Some other energy source must be actively pumping heat into the upper atmosphere, a process beyond conventional thermal models. Scientists have long referred to this as the energy crisis of ice giants, a problem seen not only on Uranus but also on Neptune. Proposed explanations include wave heating, where acoustic and gravity waves propagate upward from lower atmospheric layers and dissipate energy, as heat or Joule heating, where electrical currents induced by magnetic fields transfer energy into the atmosphere. Particle precipitation from the magnetosphere may also play a role, depositing kinetic energy at high altitudes. Webb's observations added a crucial piece to this puzzle. When the team mapped H3+ ion density alongside the temperature profile, they discovered something truly unexpected. The peaks were separated by thousands of kilometers. Maximum ion density occurred roughly 1,000 kilometers above the cloud tops, while the temperature peak appeared 3,000 to 4,000 kilometers higher. In planetary physics, this separation carries profound meaning. Ion density is driven primarily by photoionization, caused by solar UV photons, or by particle precipitation along magnetic field lines. Temperature, however, can be influenced by entirely different processes. If heating and ionization were caused by the same mechanism, peaks would coincide. Webb's data confirmed they did not. This revealed that Uranus's upper atmosphere operates on a layered, multi-process system. Heating and ionization are decoupled, each controlled by different sources and occurring at different altitudes. For decades, models assumed a single dominant process could explain ice giant atmospheres. Webb proved the reality is far more complex. Uranus is a dynamic, multi-mechanism system, with energy flowing unevenly, responding to an intricate interplay of magnetic fields, particle streams, and wave propagation, and that complexity doesn't stop at the atmosphere. Uranus's magnetic field itself is unlike anything else in the solar system. Earth's magnetic axis aligns closely with its rotational axis, tilted only 11 degrees, producing a stable magnetosphere with orderly auroral ovals. Uranus defies all of that. Its planet rotates on its side, tilted 98 degrees relative to its orbit. Its magnetic axis tilts an additional 60 degrees relative to its rotation, and the field does not even pass through the planet's center, it is offset and displaced. As the planet rotates, the magnetic field tumbles and wobbles, creating a chaotic, asymmetric magnetosphere. The result is a system so extreme that every theoretical assumption about magnetosphere-atmosphere coupling is put to the observational test. Through Webb's lens, Uranus became a natural laboratory for complex physics. The three-dimensional atmospheric map revealed two bright auroral bands near the predicted magnetic pole regions, confirming models that anticipated auroral activity along those field lines. But what shocked the team was what lay between the bands, a dark gap, a region with both depleted atmospheric glow and ion density. This band is not an artifact or imaging error. It is the direct signature of the magnetic field shaping particle precipitation, carving a visible shadow in the planet's upper atmosphere. While Jupiter also exhibits auroral features, Uranus's off-center, tumbling magnetic geometry amplifies these effects, producing asymmetries that no other planet displays. This discovery also explains the earlier thermal anomalies. The chaotic magnetic field channels energy unevenly, causing intense heating at specific altitudes while ion density peaks elsewhere. The separation of heating and ionization peaks is therefore not a coincidence. It is a direct result of Uranus's complex magnetosphere. In essence, the planet is a dynamic system hidden behind a seemingly calm, featureless blue exterior. What appears inert from Earth is actually magnetically violent, thermally layered, and structurally intricate. Why does this matter beyond Uranus itself? Ice giants like Uranus and Neptune are now thought to be among the most common planetary types in the Milky Way. Until Webb, astronomers had no detailed template for understanding them. For decades, exoplanet models relied on a single blurry Voyager snapshot from 1986. Webb has replaced that with a detailed, three-dimensional forensic map. How energy moves through an ice giant's atmosphere, how magnetic geometry controls ionospheric structure, and how multiple heating mechanisms operate across thousands of kilometers of altitude. This map is now the baseline for understanding ice giants across the galaxy. Even with these breakthroughs, the 3,0-year mystery of Uranus's cooling upper atmosphere is not fully solved. Webb provides the most complete view yet. It allows us to see the engines driving the planet's thermal behavior, trace their structure, and understand their influence on ionization and atmospheric dynamics. The next step, scientists agree, must be a dedicated probe entering the atmosphere directly. Observing Uranus from orbit is transformative, but the planet's secrets are still hidden beneath cloud tops. To fully grasp its complexity, humanity must send instruments to touch, measure, and analyze the layers Webb has mapped from afar. What Webb achieved, however, is monumental. For the first time, a true volumetric understanding of an ice giant exists. Layers of temperature, ion density, and auroral activity are no longer averaged into a single, flat measurement. The third dimension reveals not chaos, but structure. An intricate, multi-mechanism system orchestrated across thousands of kilometers. Uranus is alive with activity, operating according to physical processes that textbooks failed to anticipate, and yet fully consistent with the laws of physics once observed at sufficient resolution. In the next part, we will explore the implications of Uranus's magnetospheric chaos in more detail, how this discovery rewrites our understanding of ice giants in general, and what it means for studying exoplanets billions of miles away. We'll follow the path Webb illuminated, layer by layer, revealing the hidden symphony of forces shaping one of the most mysterious planets in our solar system. To truly understand Uranus, we must consider the planet's magnetosphere in all its chaotic glory. Unlike Earth, where the magnetic axis aligns closely with the rotational axis, Uranus spins on its side, and its magnetic field is tilted 60 degrees relative to that rotation. The field is offset from the planet's center, so as Uranus rotates, its magnetosphere doesn't spin smoothly. It wobbles, twists, and tumbles unpredictably. This extreme geometry forces the planet's atmosphere to interact with charged particles and magnetic lines in ways that defy simpler models. The auroras, the heating, And the ion density patterns are all a product of this complex dance. Webb's three-dimensional mapping has made it clear. Uranus is not a frozen, static world. It is a layered, magnetically sculpted system where multiple energy pathways coexist, overlap, and interact in a symphony of cosmic physics. The bright auroral bands revealed by Webb confirm the locations where magnetic field lines channel charged particles downward, producing visible emissions. Between these bands, however, lies a dark band where the auroras vanish. This is not empty space. It is a magnetic shadow, a region where the field configuration prevents particles from entering the atmosphere. The result is a striking visual confirmation of theoretical predictions about magnetic topology, energy transfer, and ionospheric structure. In simpler terms, the planet's own magnetic architecture dictates where energy flows and where it doesn't, creating stark structural contrasts thousands of kilometers above the clouds. This discovery fundamentally changes how scientists understand ice giants. Uranus and Neptune, the so-called ice giants, have long been treated as uniform, inert worlds. Until now, astronomers relied on the 1986 Voyager snapshot and Earth-based telescopes to model these planets. Webb has replaced this limited view with a dynamic map that captures energy flow, heating mechanisms, and magnetosphere-ionosphere coupling in 3 dimensions. No longer are these planets simple, static bodies. They are complex, multi-layered systems with physics that must be observed at sufficient resolution to reveal the hidden structures. One of the most important revelations is how energy is transported through Uranus's atmosphere. Heating and ionization are decoupled, operating at different altitudes through different mechanisms. Temperature peaks at 3,000 to 4,000 kilometers, while ion density peaks roughly 1,000 kilometers above the cloud tops. The distance between these peaks confirms that multiple independent processes are simultaneously at work, each with its own energy source. This is a striking validation of theoretical models that predicted such multi-mechanism behavior, but until Webb, there was no observational evidence. Now, the data provide a blueprint for how ice giant atmospheres function under extreme magnetic conditions. The implications extend beyond Uranus itself. Ice giants are among the most common planet types in the galaxy, and astronomers have discovered hundreds of exoplanets that fall into this category. Until Webb, these distant worlds were modeled based on assumptions derived from a single Voyager snapshot. Now, with a detailed three-dimensional map of Uranus, scientists have a physical template to study exoplanet atmospheres, magnetic interactions, and energy transport. The map reveals how temperature and particle density are layered, how magnetic geometry affects auroral structures, and how multiple heating mechanisms operate in parallel. For the first time, there is a concrete reference for understanding billions of ice giant exoplanets throughout the Milky Way. Webb also resolved one of the enduring mysteries of Uranus's long-term cooling trend. For decades, observations showed that the planet's upper atmosphere was cooling systematically over 30 years, defying expectations based on solar heating alone. Webb's data reveal that the chaotic magnetosphere is unevenly distributing energy, explaining why different layers experience varying heating rates. The multi-mechanism nature of the energy flow accounts for both the cooling trend and the localized warming at higher altitudes. Uranus's atmosphere is not in equilibrium. It is a dynamic, interacting system shaped by magnetic forces, particle precipitation, and wave-driven heating. The broader significance of these findings cannot be overstated. Understanding Uranus allows scientists to test theoretical models under extreme conditions. The planet's tilted rotation, off-center magnetic field, and asymmetric magnetosphere provide a natural laboratory for studying energy transfer, atmospheric dynamics, and magnetic coupling. Observations from Webb will refine models used to predict the behavior of ice giant exoplanets and improve our understanding of planetary atmospheres in general. This is a rare opportunity in planetary science, to witness complex physics in action on a world so different from our own. Webb's 1.5-hour observation window also captured rotational effects, showing how the magnetic field and atmospheric heating evolve as the planet spins. The tumbling magnetosphere produces time-dependent auroral variations, while wave-driven and particle-driven heating create localized hot spots. These patterns highlight the need to treat ice giant atmospheres as dynamic systems, not static averages. Previously, scientists could only guess at these processes. Now they can map them, layer by layer, altitude by altitude, in 3 dimensions. Uranus is no longer the cold, lifeless planet described in textbooks. It is a symphony of physics operating across thousands of kilometers, orchestrated by a magnetic field that defies conventional rules. Its auroras, temperature gradients, and ion density peaks are all expressions of a complex system in constant interaction. This has profound implications for planetary science, exoplanet studies, and our understanding of magnetically driven atmospheres. The discoveries made by Webb are not just observations, they are a paradigm shift. In the next and final part, we will explore what these findings mean for future exploration, the necessity of dedicated probes to Uranus, and how this new understanding will shape the study of ice giants both in our solar system and across the galaxy. We will see why Webb's observations are just the beginning, and why the true story of Uranus is only now unfolding. The story of Uranus is far from finished. Webb has lifted the veil, revealing a planet that is far more dynamic, layered, and magnetically violent than any textbook suggested. Yet, the telescope can only observe from afar. While it has mapped the atmosphere in 3 dimensions, revealed temperature gradients, ion densities, and auroral patterns, it cannot probe the lower atmospheric layers, the deeper cloud decks, or the subtle processes that drive these mechanisms from within. To fully understand Uranus, humanity must take the next step, a dedicated probe, a mission to descend into its atmosphere, to measure, sample, and analyze the layers Webb has exposed from orbit. Such a mission would be unprecedented. It would require instruments capable of withstanding extreme temperatures, high pressures, and intense radiation, all while capturing data on magnetic fields, particle fluxes, and chemical composition. But the reward would be extraordinary. For the first time, we could directly observe the engines that drive Uranus's energy dynamics, test theories about magnetosphere-atmosphere coupling, and validate models for ice giants across the galaxy. Webb has given us the map. A probe would allow us to step onto the path it has illuminated. The implications extend far beyond one planet. Ice giants like Uranus are among the most common types of exoplanets in the Milky Way. Yet, until now, we had only the faintest hints of how they function. Every exoplanet discovered with similar mass and radius was modeled based on a single, blurry snapshot from Voyager 2, combined with Earth-based assumptions. Webb has changed that, providing a 3-dimensional template showing how energy flows, how magnetic geometry sculpts ionospheric structure, and how layered heating mechanisms operate simultaneously across thousands of kilometers. Scientists can now apply this physical baseline to study ice giants across the galaxy with confidence. Even within our own solar system, this discovery challenges fundamental assumptions about planetary atmospheres. Uranus is not simply cold and inert, it is a complex, dynamic system, orchestrated by multiple independent processes interacting across layers of atmosphere and magnetosphere. The separation of ion density and temperature peaks demonstrates the presence of distinct energy sources, each operating independently but interacting within the planet's layered structure. Auroral bands, magnetic shadows, and chaotic rotational effects illustrate a magnetosphere unlike any other in the solar system, a natural laboratory for extreme physics, where theory and observation meet in real time. Webb's observations also redefine our understanding of planetary evolution. For decades, Uranus's cooling upper atmosphere presented a mystery. Continuous temperature decline over 30 years suggested unknown energy sinks at work. Now, we see that the chaotic magnetic field redistributes energy unevenly, while independent heating processes operate at different altitudes. Uranus's thermal state is not static, it is dynamic, evolving, and intimately tied to its magnetic and rotational properties. These insights challenge models of planetary cooling, atmospheric circulation, and energy balance for all ice giants, not just Uranus. This discovery has broader philosophical implications as well. For years, Uranus was dismissed as a bland, unremarkable planet, a distant, frozen world with little to teach us about planetary physics. Webb has overturned that assumption entirely. Uranus is now understood as a richly layered system, its secrets hidden beneath a deceptively calm surface, waiting for the right tools to reveal them. It reminds us that even planets we think we understand may hold surprises, and that science is often a process of peeling back layers of assumed simplicity to reveal deeper complexity. Looking forward, Webb's map sets the stage for decades of exploration. Future missions can now target specific atmospheric layers, auroral regions, and magnetospheric interactions for closer study. Scientists can simulate energy flow more accurately, refine models for ice giant exoplanets, and test hypotheses about atmospheric dynamics that previously seemed inaccessible. Uranus has become the Rosetta Stone for understanding a class of planets that dominate our galaxy, bridging observational astronomy, theoretical physics, and planetary science in unprecedented ways. Ultimately, what Webb has achieved is a reminder of the power of exploration and technological innovation. The telescope transformed Uranus from a distant, featureless blue dot into a laboratory for understanding extreme atmospheric physics. It has shown us that complex systems exist, even in places we once assumed were simple, and that the universe still holds mysteries that challenge the foundations of our knowledge. Each new dataset, each new observation, peels back another layer of reality, revealing intricate mechanisms hidden in plain sight. The story of Uranus is far from over, but thanks to Webb, humanity now has the tools to follow it deeper than ever before. From the chaotic magnetosphere to the layered temperature gradients, from auroral bands to invisible magnetic shadows, we can see the engines behind the planet's dynamics for the first time. The telescope has provided the map, and the next generation of missions will bring us to the planet itself, unlocking secrets that will redefine planetary science for decades to come.